Welcome to the Blueprint Room. I'll be your chief architect for today's workshop. Right off the bat, I want you to visualize two things in your mind: a structural integrity bar tracking your mark potential from 0 to 100%, and a construction deadline clock, which is your exam timer ticking down. Now, I had to ask you a serious question. Why is it that so many students' exam structures completely collapse under the pressure of unfamiliar mechanics contexts? You know exactly what I'm talking about. You walk into the Cambridge AS and A-Level Mathematics 9709 paper. You look down at a problem involving equilibrium, and suddenly the entire mathematical skyscraper you thought you had perfectly designed in your head just crumbles into dust. It's a disaster. And look, it happens because students are trying to build with weak cement and misaligned steel. Today, we are going to dive deep into this. We are going to fundamentally change how you engineer your answers, step by step, so that your exam structure is absolutely unshakable. To truly understand why these academic structures collapse so frequently, we need to take a hard look at the workforce on the ground. I want you to imagine we have two junior builders on our construction site right now. Builder 1 is Alex. Now, Alex works hard, but Alex loves to just stack heavy bricks of raw facts. He memorizes every single formula in the textbook and just dumps them all onto the exam page. Force equals mass times acceleration. Friction is mu times r. He just throws it all down, completely failing to check if the steel frame of his argument can actually support that massive, unorganized weight. Then, on the other side of the site, we have Builder 2, Sam. Sam has a completely different problem. Sam wants to put up shiny glass panels and decorative features. Sam uses all this fancy terminology and sophisticated phrasing before ever cementing the foundational columns. Sam entirely misses the core command words of the question. Both of these approaches result in catastrophic structural failure. You literally cannot build a skyscraper like this. But I promise you, by the end of this explainer, I'm going to reveal exactly what the Cambridge examiners are really looking for. We're going to stop losing easy marks on vector sum zero problems, and you are going to learn how to lay down a load-bearing response that survives the toughest grading stress tests. So here is our project blueprint for today's build. First up, we're going to pour the foundation, which means reviewing our core principles. Second, we'll erect the steel frame through a rigorous methodology. Third, we're going to review the building code by looking at actual examiner warnings. And finally, we'll conduct a final inspection using context analysis. Let's move right into part 1, the foundation, core principles. Before you can even begin to think about calculating tension or resolving friction or dealing with inclined planes, you absolutely must have a flawless bedrock grasp of the concepts. And what is truly fascinating here is how incredibly simple the core principle actually is, yet how frequently it gets totally misinterpreted under exam pressure. Equilibrium, specifically in the context of mechanics, means a vector sum of 0. It is the state where the systematic analysis of all vector forces acting on an object equals a net total of exactly 0. This is your bedrock. The entire theoretical architecture of your exam response rests completely on these precise mathematical definitions and their causal relationships. If your foundation is cracked here, everything else above it falls, period. Think about the command stress points enforced by the examiner reports. If the command word in the prompt asks you to evaluate or show that, and you just casually describe the forces like you're telling a story, your building collapses instantly under the weight of the mark scheme criteria. You have to align your mathematical paragraph columns perfectly with the command grade. You see, there are 3 distinct cognitive domains targeted by the assessment objectives in this syllabus. These are the basic building blocks of any successful Cambridge response. First, we have knowledge and understanding. Do you actually know what a normal reaction force is? Do you know the exact formula for limiting friction? Second is application. Can you take that theoretical knowledge and apply it to a real scenario, like a particle resting precariously on a dangerously steep inclined plane? And third, we have analysis. Can you resolve those forces mathematically to prove beyond a shadow of a doubt that the vector sum is indeed 0? You cannot skip a single one of these domains. If you just show knowledge but skip the analysis, you've essentially built a 50-story skyscraper without installing any internal staircases or elevators. It might look okay from the outside, but it's completely non-functional, and the examiners will fail the inspection. And here is a crucial architectural secret. The principal examiner reports explicitly highlight that candidates who reference cross-topic connections achieve significantly higher marks. Think of these connections as the vital mortar holding all your foundational knowledge together. Mechanics does not exist in a vacuum. Your ability to bring in pure math concepts, like utilizing advanced trigonometry for resolving tricky angles or deploying calculus for kinematics within a mechanics problem, shows the examiner that you aren't just memorizing disconnected facts. It proves you are a master architect. It shows you understand exactly how the plumbing, the electricity, and the structural steel all interact within the exact same building. Which brings us perfectly to part 2, The steel frame methodology. Now that our concrete foundation is cured and solid, we need a strict procedural framework. I want to take you back to the drafting board for a minute, back to our two junior builders, Alex and Sam. I hear them debating the ironwork right now. Alex is saying, look, for the first step, let's just write down the friction formula everywhere and hope one of them gets a mark. And Sam pushes back, saying, no, we need to leave a hollow space for a dynamic counterargument about the esoteric nature of equilibrium to really hit those top band scores. And as the chief architect, I have to step in and stop both of them. You cannot build like that. We have a strict 5-step methodology to rivet this steel frame together. Step 1, identify given information. You extract the exact data from the text and tables, no guessing. Step 2, break into logical steps. You resolve your forces horizontally, then you resolve them vertically. Step 3, solve systematically. You execute your analysis with crystal clear working out. Step 4, check reasonableness. Verify your results. Does a tension of 10,000 newtons on a tiny light string actually make sense? Probably not. Step 5, make justified recommendations or conclusions based strictly on that calculated evidence. You have to write your entire skeleton out to comply perfectly with these examiner guidelines. Each one of these 5 steps is a bolted joint in your structural frame. You miss a bolt, the wind blows, the whole building falls. This strictly sequenced process brilliantly illustrates the method mark strategy. In Cambridge 9709 mechanics, marks are heavily awarded for process and systematic execution. I need you to really hear this. The examiners award points for the procedural process, for the clear working, for the step-by-step unrolling of your logic. They do not just care about the shiny glass panels of your final perfect answer. If you use the correct methodology, if you set up the vector sum zero equations perfectly, but you make a tiny, silly calculator error at the very end, this method mark strategy acts as your structural safety net. You will still get the vast majority of the marks because your steel frame was fundamentally sound. So never ever hide your working out. Your working out is the visible ironwork that the examiner is inspecting. Show them the steel. Let's move into part 3, building code examiner warnings. All right, time for a mid-build site inspection. Before we secure this high-scoring paragraph framework and pour the final layer of text concrete, I need to make sure your construction line is reinforced. Subscribe to Ace the Exams right now and turn on all notifications to receive our weekly structural grade upgrades. Whether you are building an IGCSE foundation or setting up an A-level skyscraper, this channel is your primary grid. Okay, inspection over. Let's get back to the site. We need to rapid-fire the top 3 building code violations that consistently cause candidates to hemorrhage easy marks on this specific paper. Violation 1, forgetting proper format conventions. This means failing to use proper headings, botching your terminology, or just having zero clear annotation on your force diagrams. Violation 2, failing to check format and presentation. Your math might technically be right, but if your page looks like a bomb went off in a math factory, the examiner cannot trace your load-bearing columns. You get 0 marks for a tangled mess. And violation 3, the absolute classic structural flaw, providing generic answers not specific to the context given. When our builders hit an unexpected structural roadblock mid-paragraph, it's usually because their evidence beam is failing to latch onto the main thesis column. To fix this, you have to upgrade your cement. You must use the PL methodology: point, evidence, evaluation, link. You make your mathematical points, you back it up with calculated evidence, you evaluate what that means for the equilibrium, and you link it directly back to the specific scenario of the question. You have to rivet the data to the evaluation. Let's look at this in practice. Consider these 2 different approaches on the site. On the left, Builder A presents a structurally unsound answer. It's exactly what we talked about, just heavy bricks of raw, generic facts. Builder A writes, forces up equals forces down, friction opposes motion. Now, is that true? Yes, but it's completely unattached to the specific particle on the specific slope with the specific coefficient of friction mentioned in the exam prompt. It's floating in midair. On the right, we have Builder B. This is a perfectly engineered response. It methodically applies the vector sum zero principle using that Peel method we just talked about to successfully latch calculated evidence onto the highly specific question context. Builder B writes, because the particle is in limiting equilibrium, the maximum frictional force of 15 newtons directly balances the downward parallel component of weight, resulting in a vector sum of 0. Look at the difference. That is a load-bearing sentence. That sentence can hold up the entire weight of the mark scheme. This takes us to our final section, part 4, final inspection, context analysis. We now have to focus on the critical evaluative thinking required to survive the examiner's ultimate stress testing. The syllabus specifically states that data interpretation skills are absolutely critical. You must be able to extract data, interpret relationships, and draw evidence-based conclusions. Top-scoring candidates demonstrate elite evaluative thinking, and here's exactly how they engineer it. They question assumptions immediately. They look at the prompt and ask, wait, is the string really light and inextensible, or do I need to account for mass? They consider different perspectives. They justify every single decision with hard mathematical evidence. When they do a comparative analysis, they identify similarities and differences using proper comparative connectives, and they support every single point with data. And finally, they draw conclusions on relative importance. This kind of robust comparative analysis acts as reinforced rebar running straight through your concrete. It secures the maximum possible top band marks. If you just state facts without evaluating their impact on the overall system's equilibrium, your concrete will inevitably crack under the examiner's red pen. I want to highlight this quote directly from the syllabus because it is literally everything. Top-performing students exhibit connected, conceptual understanding transferable to unfamiliar contexts. I want you to really focus on that word unfamiliar. The Cambridge examiners are not going to give you the exact same building to construct every time you sit down for a paper. They are going to change the soil. They are going to change the wind speed. They are going to change the construction materials. Adaptability to new, weird, unfamiliar contexts is the true ultimate test of your exam's structural integrity. If you only memorize how to build a wooden shed and you walk into the exam and they ask you to engineer a steel suspension bridge, you will fail. You will fail unless you understand the core underlying principles of vector sum zero so deeply and so conceptually that you can apply them anywhere, under any conditions. So I am now initiating a live site safety audit right here, right now. This is your blueprint matrix rebar stress test. The next time you sit down with a complex past paper and you see a massive source data chart, a tricky graph, or a dense text layout, I am challenging you. Start a 60-second countdown clock. Within that first minute, force yourself to extract the single most high-yielding core metric needed for your construction. Ask yourself honestly, are your vector sum zero calculations just generic math floating in space like builder A, or are they load-bearing arguments inextricably linked to the specific context of the question like builder B? If you can't answer that with absolute certainty, you need to go back to the drafting board and practice your past papers using this exact architectural framework we laid out today. Secure your foundation, check your steel, and whatever you do, don't let your high-rises collapse. Build it right.